Hello, everyone. First of all, I would like to say a big thank you to the Lumiere Research Program for providing me this opportunity to engage in one of the most memorable experiences in my life. My name is Anik Punchihewa. I'm from Sri Lanka and I'm based in Colombo. My research question was on how Z mu mu decays show us how we can study the properties of unstable particles by looking at the stable particles to which the unstable particles decay into. For a bit of background pertaining this topic, most unstable particles usually go out of existence almost the instant they come into existence. And this makes it quite difficult for us to understand and analyze its properties because they don't have enough time to reach the sensitive parts of particle detectors. However, prior to these unstable particles going out of existence, they actually usually decay into relatively more stable products. And we can usually very comprehensively study the properties of these stable products. And therefore, by looking at the properties of these stable products, we can try and understand the properties of the unstable particle from which these stable particles decayed from. In the context of my research paper, I focused on studying the properties of an unstable particle known as the Z boson. The Z boson can decay into a wide range of particles. However, I focused on its decay into two muons. The muon is a relatively more stable particle, and this particle decay is simply known as Z mu mu decay, or it's also just depicted with a Z arrow mu mu, which basically means the Z boson decaying into two muons. For a bit about the type of methodology and the analysis that I followed, my research paper followed a data analysis methodology. I focused on particle interactions at the Large Hadron Collider, or the LHC at CERN, which is the biggest particle accelerator in the world. And I used its data sets at its biggest detector, the ATLAS detector. And I used these data sets obtained from the ATLAS website. And I used a software known as Root, which is being developed by CERN, to help compile a series of histograms plotting various properties of the two muons in the Z mu mu decay as variables. In these histograms, there were two types of simulations shown. One was known as the data simulation, which was data based on real-world interactions that we actually observe. The next one is the Monte Carlo simulation, which is a simulation based on predicted models and theories that we predict prior to actually observing real-world data. So by having these two simulations, we can compare and contrast them to just see how effective and accurate our theoretical models are and help improve them for future models built on particle interactions. The two simulations may or may not always agree with each other. Finally, upon completion, we can observe not just data about Z boson, but about the ATLAS detector itself by looking at peaks and dips in these histograms, which is evident in this slide. In this graph that we observe, we see a peak at around 90 GeV. GeV is another unit for measuring mass. And in this histogram, we're plotting the invariant mass of the two muons on the x-axis, while its number of events are plotted on the y-axis. The term invariant mass simply refers to the total mass of the two muons measured with respect to different situations. And when this invariant mass is equal to about 90 GeV, we see a large number of events, more than any other invariant mass that we see, which indicates that this is the most probabilistic outcome. And hence we take this value, 90 GeV, to be the value of the Z boson's invariant mass. Because in a particle decay, when the Z boson decays, its mass gets converted and divided amongst the two muons. And hence this should be the most accurate value for the mass of the Z boson. A similar thing was done not just for invariant mass, but for energy, momentum, and a range of other variables. Finally, there was a degree of inaccuracy in these results, which is brought about the fact that in this research paper, we were assuming that it's just a Z boson decaying into two muons, and that was the end of the story, which may not always be the case, as these muons could further decay into a photon, which could carry away some of the energy from the muons, bringing about a sense of inaccuracy in these results. Finally, the study from these two muons proved to be quite effective to help us understand key properties of the elusive Z boson. However, we shouldn't stop here. We should continuously, perpetually analyze and understand these attributes. It's also important to look at the Z boson's decay into maybe other particles and compare results from those research discussions and compare them to Z mu decays to better enhance our understanding of the Z boson. That about concludes my research paper. Thank you so much for listening. I hope you all understood, and I hope you have a great day. Thank you.